So, hello everyone. I am Vivek Kumar Srivastav, research scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology. So, I am basically TA of this course, and this is the problem solving class, as you all know. So, before going ahead, let us see that what we have done in the previous class. So, in the previous class, we have basically solve some of the numerical based on the lossless transmission line, which is covered in the first week of the course. Okay, so in the today's presentation or say today's class, we will see the problem based on the lossy transmission line. Okay, so if you have any doubt, then you can ask your doubt during the session. Okay, okay, so I'm going to start the session. Yeah, so this is the first numerical. So the problem is the measured VSWR of a transmission line is 5 and has a characteristic impedance of 50 ohm. Determine the value of load impedance connected to the transmission line. Yeah, Sunil Gupta, yes. Please ask your doubt. Okay, sure.
Sir, will the notes be available for this?
Yes, yes. Actually, this will be provided by NPTEL team.
Oh, okay, sir. Thank
Yeah,
you.
yes. So, like SWR, first of all, is defined as V max over V min. So, as I said earlier, V max is defined as V naught plus e raised to the power minus j beta z in bracket 1 plus gamma L. Okay, phase term will be 0 here. Sorry, phase term will be 1 here. Okay. Similarly, V min is defined as V naught plus e raised to the power minus j beta z in bracket 1 minus mod of gamma. Okay, so this term will be cancel each other. So SWR is defined as 1 plus mod of gamma over 1 minus mod of gamma. Okay, so by using this formula, we will first calculate the value of reflection coefficient. So here I am taking the inverse relation. Okay, so gamma is calculated as S minus 1 over S plus 1, where S define the VSWR, which is 5 here. Okay, so now put this value of S here. So gamma is 4 by 6, which is equals to 2 by 3. Okay, so now you have got the value of gamma. So now you can use this formula of reflection coefficient, that is Z is equals to ZL minus Z naught over ZL plus Z naught. Okay, so ZL here is, you have to find out, Z naught is mentioned as 50 ohm. So this will be 2 by 3 ZL minus 50 over ZL plus 50. So after calculating the value of ZL, you will find as 10 ohm. Okay. Any doubt in this question?
No, sir.
Okay. So this is the second question we have. A 75 ohm coaxial line has a current of 1.8 cos of omega t minus beta z milliampere. Okay. Determine the frequency, phase velocity, wavelength, relative permittivity of line, phasor form of the current, and the time domain voltage on the transmission line. Okay, so
Yes, sir.
uh, for solving such type of question, we have to equate this current equation with the standard current equation, that is I of t comma z is equals to I naught cos over omega t minus beta z. Okay, so after equating we have found that omega is defined as 3.77 into 10 raised to the power 9. Okay, so this will become equals to 2 pi f. So from here you can calculate the value of f, which is equals to 600 megahertz. Okay, so the second question is phase velocity. So for finding out the phase velocity, you have to differentiate this phase term with respect to time. Okay, so omega t minus beta z represent the phase term. So you have to just take the derivative of this. So this will become omega minus beta z, and this will be becomes equals to 0. So from here you will find sorry, dz by dt. Okay, so this will becomes phase velocity. Okay, so phase velocity vp becomes equals to omega over beta. So from here you can calculate the value of phase velocity. So now the after that the wavelength we can calculate as, see, wavelength, how can we define wavelength? Any idea?
So from the velocity by frequency also we can get.
From the velocity over frequency. Yeah, that's correct. But if suppose this is a sinusoidal wave, sinusoidal wave, so how will you define the uh, this wavelength? What is
2
wavelength
pi
here?
by beta.
So
2 pi by
basically,
beta is also correct. Yes.
yes. So basically, wavelength is defined as a distance between two creased or thought. Okay. So this defines the wavelength lambda. Okay. So just put this cos of omega t minus beta into lambda. So this phase will be equals to 2 pi, because for a sinusoidal signal we know that this uh, difference will be equals to, phase difference will be equals to 2 pi. Okay, so we define beta into lambda is equals to 2 pi. So from here we can calculate the value of lambda is equals to 2 pi over beta. Okay, so beta you have already known, okay, which is equals to 18.13. Okay, you have to just put the value of beta here, and after that you can calculate the value of lambda. Okay, so after that the
Yes, sir.
relative permittivity of the line. So relative permittivity, for calculating the relative permittivity, as we know that phase velocity can also be defined as a 1 over a square root of LC. Okay, so if suppose this line is in the air, okay, then here the relative permittivity and relative permeability is equals to mu naught and epsilon naught. But as the line is made up of some material, so there should be some permittivity associated with it. Okay, so that's why here we can write it like root over L1 C1 into root over epsilon R. Okay, so this will be equals to C over root over epsilon R. So from this equation you can calculate the value of epsilon. Okay, any doubt?
This actually comes from like V is equal to root over mu upon epsilon, right?
Yes, actually, see, if here we are actually using circuit analysis, no? So in case of
Hmm.
circuit analysis, we can say like L is proportional to mu, okay, and C is proportional to epsilon, okay. In case of field, we will define these parameters, whereas in case of circuits, we will define these parameters, okay. So they are
Okay, okay,
yeah, they are like mutually dependent, just like, okay. So
okay, okay.
that's how we can calculate the value of epsilon. So after
Hmm.
that, phasor form of current he is asking. So as we know that in case of phasor current, we have to remove this time dependence term, okay. So first of all, let us define this in phasor term. So I of z is t comma z is also defined like 1.8 e raised to the power j beta z, oh sorry, beta t minus this omega t minus beta z, okay. So if suppose we want to use this signal, so we have to take the real part of this signal, okay. And to to obtain the phasor form of this current, we have to omit this time dependence term, okay. So this can be
Hmm.
written as 1.8 into e raised to the power minus j beta into z. So beta you already know, you have to just replace the value of beta here. So this represent the phasor form of the current. Now after that, we can also calculate the value of time domain voltage representation, which is he is asking. So for that,
Hmm.
uh, line voltage is defined as line current times characteristic impedance of the transmission line, okay, which is 75 here, okay. So
Hmm.
you have to multiply these two terms, okay, means this ij with 75, and you will got this answer. So any
Okay, sir.
problem, any issue with this numerical?
No, sir.
Okay. So the third question is, consider a 50 ohm lossy transmission line with attenuation constant alpha is defined as 0.01 dB per meter, and the phase constant is 0.8 pi radian per meter. If the operating frequency is 100 megahertz, calculate the value of line parameter. Okay. So for solving such type of problem, we first of all we have to know that for how to define characteristic impedance for a lossy transmission line, and the propagation constant, because propagation constant basically define the alpha plus j beta term, okay. So in case of lossy transmission line, z naught is defined as root over r plus j omega l upon g plus j omega c,
Hmm.
whereas propagation constant is defined as r plus j omega l into g plus j omega c, okay. So by using these two equation, we have to solve this numerical, okay. So let us see. So as I said, z naught is defined as r plus j omega l over g plus j omega c, okay. So here you can see, if suppose we will solve this equation, so we will get real part plus imaginary part, okay. But in this numerical it is shown that the characteristic impedance is real only. Okay, so how to get this real part, that we will see. So z naught is equals to root over r plus j omega l upon g plus j omega c. Okay, so let us take this l and c common here. So z naught is defined as root over l by c in bracket r by l plus j omega over g by c plus j omega. Okay, now to cancel these term, there must be a condition, that is r by l should be equals to g by c. Then only these terms will be cancelled and this z naught will be real. Okay, so let us assume this condition is satisfied. So this z naught is defined as root over l by c. Okay, similarly, and also this will be equals to 50 ohm. So this is our first equation. Okay, so let us move ahead and find the value of gamma. So gamma is defined as root over r plus j omega l into g plus j omega c. Okay, so similarly you have to take l and c common here. So this will be defined as root over lc into r by l plus j omega into g by c plus j omega. Okay, so as we know that r by l is equals to g by c, so you have to replace the value of g by c here. So this will becomes r by l. Okay, so we can define it like root l by c, sorry, root lc. So this term becomes a square, so this will come out of this square root. So this becomes r by l plus j omega. Okay, so now multiply this root over lc in these two terms. So sorry, you will get r root over l by c plus j omega root over lc. So this represents the alpha term which is given here equals to 0.01, and b phase sorry, imaginary term which is the phase constant is given here 0.85. Okay, so you have to just equate these uh, terms with their respective values, and you have to just solve for these three values, that is l, c and r. So the value of r you will get 0.2 milliohm, l is 0.2 microhenry per meter, c is 80 picofarad per meter, and the value of g you can calculate by using this equation. Okay, so here I think I have written wrong, so you can correct it by yourself. Okay, you can use this uh, relationship for finding the value of g. Okay, any doubt in this
Okay.
question?
Okay. Sir, here in alpha,
Yes,
which is given as 0.01 dB per meter,
yes.
we will take the dB per unit meter part or Nepper per meter part, sir?
Nepper per meter. Nepper per meter you have to take in.
Nepper.
Yes,
Okay. The conversion has to be done.
yes, yes.
Okay. Okay.
So the next question is, a radio transmitter is connected to an antenna having an impedance of 80 plus J40 ohm with a 50 ohm coaxial cable. Okay, so if suppose this is the coaxial cable and this is connected to a load of this 80 plus J40, and this characteristic of this line, coaxial line, is 50 ohm. If a 50 ohm transmitter is delivered 30 watt when connected to a 50 ohm load. Okay, so if suppose you have this source, okay, and you will directly connect it to this load. ठीक है? So the impedance of this transmitter is, let us suppose, 50 ohm as given in the question, and this is also 50 ohm. So you can see here that uh, this will be matched, this system will be matched. Okay, so there will not be any reflection. So the whole power delivered, that is the whole transmitter power will deliver to the load. Okay, so there will not be any reflection here. Okay, so you can say like input power to this load is equals to 30 watt. Okay, so the question is asking like when you will connect this load to a transmission line, okay, and you are using the same source at this input of this transmission line, then how much power is delivered to the antenna, which is the load here. Okay, so any idea that how to proceed? Okay, so
I'm not clear with the question actually. So
yes,
two
yes,
parts are given. I mean,
yes.
one is given that the radio transmitter is connecting to antenna, and the other is these are two different sources, or
See, the source is same here, which the source which is
Mhm.
defined here, the same source right now I am applying to this transmission line. So you have to find out that how much power it is delivered to the load, which is antenna here.
Okay,
Okay, this is just an example. He is saying like when this source is connected to the load directly, having the same impedance, okay, then this source will deliver 30 watt power to the load. So now if suppose this
okay,
same source I am using to feed this transmission line, then how much power it will transmit to the load. Okay,
okay.
so now it's clear.
Yes, sir.
Okay, so for calculating load power from this question, you have to use the relationship that is PL is equals to 1 minus gamma square into P in. Okay, so by using this relationship you can find out the value of load power. So for see here you have the value of P in. Okay, the value of characteristic impedance of the line and the load impedance is already given. So by using this you can calculate the value of gamma here. Okay, after that you can calculate the
Mhm.
value of load power. Okay, so see gamma you can calculate as ZL, which is at t plus J40. Okay, Z naught is 50. Okay, so by using this relationship you can obtain the value of gamma, which is equals to 0.36 magnitude and phase is 36.02 in degree. Okay, and input power is given as 30 watt. So now you have to put the value of gamma here and P in here. You will directly get the value of load power. Any doubt?
Sir, how this input power we have taken from the second case, sir?
See, you can read the question once. He is saying like if the 50 ohm transmitter can deliver 30 watt power when connected to a 50 ohm load. Okay, so he
Yes,
is
sir.
giving an example like if suppose you have a source, okay, and this source have a internal impedance of 50 ohm. Okay, and now you want to connect this source to a load having a value of 50 ohm. Okay, so tell me how much reflection you will get at the source side.
No reflection.
No reflection. So it means that whatever power delivered by the source, the same load will get. Okay, because there is no reflection.
Okay.
Okay, so that's how you can calculate the value of P in.
Okay. Okay. That is the, I mean, the power delivered by the source.
Power delivered by the source or power input to the transmission line.
Okay. Okay.
Both are same here. Like here you can see, here you have to connect the source. Okay, so uh, the transmission line will get the same amount of power which is delivered by the load itself. Any other doubt? Okay, so this is the next question. A transmission line having a characteristic impedance of 300 ohm is terminated by a purely capacitive reactance of minus j 300 ohm. So like here is the transmission line, and it is terminated by a purely capacitive load, and the value of this load is minus 3 j 300 ohm. Okay, and the impedance of this line is 300 ohm. Okay, consider the wave velocity is 2.5 into 10 raised to the power 8. The frequency of operation is 100 megahertz, and the length of the transmission line is 2 meter. Okay, then calculate the reflection coefficient VSWR and power delivered to the load. Okay, so for proceeding such type of question, you have you have to first calculate the value of reflection coefficient. Okay, because anyway power delivered to the load is dependent on reflection coefficient. VSWR is also dependent on the reflection coefficient, so you have to first calculate the value of reflection coefficient here. Okay, so reflection coefficient, as I say, it is defined as gamma is equals to ZL minus Z naught over ZL plus Z naught. So the value of ZL is given here, minus J 300, and Z naught is 300. So you can calculate it like, yeah, minus 300 you have taken common, then the remaining part is 1 plus J. Here you can take 300 common, so this will become 1 minus J. So this will be cancelled. Okay, so now you can multiply with the conjugate of this denominator, which is 1 plus J, and this will also 1 plus J. So this becomes 1, uh, yeah, 1 minus 1 plus 2J over 1 plus 1. Okay, so this will cancel, and yes, so this 2 will cancel, so this becomes minus J. Okay, so see, anyway this minus sign, I think ZL minus Z naught over ZL plus Z naught. Yeah, so I think I have written this wrong. I think this will becomes 1 270, I think. Okay, so anyway this phase term will not affect here, so you can calculate the value of VSWR 1 plus gamma over 1 minus gamma, so this will becomes infinite. Okay, because magnitude of gamma is equals to 1 here, so here in denominator this will become 0, so the VSWR becomes infinite, means you will get full reflection. Okay, similarly, to calculate the value of load power, okay, you have to uh, first check that what will be the input impedance at this port. at the input port. Okay, you have to first calculate the value of input impedance. So here you can use this formula for calculating the value of input impedance, which we have already used in the previous class as well. So Zin is equals to Z naught, which is 300 ohm. ZL is defined as this. Okay, and beta L you can calculate as 2 pi over lambda, and lambda becomes V by F. V is 2.5 into 10 raised to the power 8 divided by 10 raised to the power 8. So this becomes 2.5. Okay, so beta will be equals to 0.8 pi. Okay, and L is given here 2 meter. So by using these two parameter you can calculate the value of beta L. So this will become 288 degree. So now you can put the value of beta L, ZL and Z naught here, and after calculating you will get the value of Zin is equals to J 589 ohm. Okay, so here you can see that at the input side you will get 589 ohm. Okay, which is imaginary. Okay, this means that if suppose a source is connected here, okay, so the real power can be delivered to the load if the input impedance seen by this port is real, then only real power will be delivered. But as the source is seeing imaginary impedance, so no power will be delivered to the load. Okay, so that's how you can calculate the value of load power. So here basically load power is 0, real value will be 0. So any doubt in this question?
No.
Okay, so this is the next question. A transmission line having a length of 2 meter and a characteristic impedance of 300 ohm is used to connect the source to a 150 ohm load. So here is the transmission line having length of 2 meter. The characteristic impedance is 300 ohm, and this basically used to connect the load of value 150 ohm. Okay, the source has a voltage of, so here is the source basically having a voltage of 60 volt, and the internal resistance of uh, 300 ohm. So here is the internal resistance of the source, which is equals to Rg. The operating frequency is 100 megahertz is used to feed the transmission line. Consider the wave velocity is this much. Okay, determine the position of maxima and minima of the traveling voltage. Okay, so for proceeding this question you have to first see the uh, voltage equation for a transmission line. So Vz is defined as V naught plus e raised to the power minus j beta z in bracket 1 plus mod of gamma e raised to the power j 2 beta z plus phi. Okay, so for obtaining maximum voltage on this transmission line, this phase turn should be equals to 1, and this can only be possible if the term 2 beta z plus phi becomes equals to integer multiple of 2 pi. Okay, so if suppose you will get the integer multiple of 2 pi, then only you will get the maximum voltage. Whereas for obtaining the minimum voltage, here let me right, is maximum value, and here for obtaining the maximum minimum voltage, this phase turn will be equals to -1. Okay, so this can only be obtained when this will be equals to odd multiple of 2 pi, or say pi. Okay, so that's how you can yeah, so that's how you can calculate the maximum voltage and minimum voltage, and by using this relation you can find the location of maxima and minima. Okay, so see, for obtaining the value of maxima and minima, you have to first, yeah, so here I can simplify it like z max is equals to 1 over 2 beta, okay, in bracket minus phi plus 2 pi m. Okay, so the same equation I am using here. Yeah, so basically if pi can be a positive integer, negative integer, sorry, m can be a positive or negative, it doesn't matter because anyway the value becomes 0. Okay, so that's how you can use this equation to calculate the maximum value. Okay, so for that you have to find the value of beta and phi. So for obtaining the value of phi, as you know that gamma is defined as ZL minus Z naught over ZL plus Z naught. Okay, so you can put the value of ZL and Z naught as given in this equation. ZL is, oh sorry, in this question that ZL is 150 ohm and Z naught is 300 ohm. So by using this relation, you will get gamma is equals to minus 1 by 3. So this represents that the magnitude is equals to 1 by 3, whereas the phase is equals to 180 or say pi. Okay, and for obtaining the value of beta, as I said in the previous example, 2 pi by lambda, and lambda here is same as the previous question because these parameters are same here. So 2 pi by, yeah, 2.5. Okay, so this becomes 0.8 pi. Okay, so you have to just put the value of beta and phi here so as to obtain the value of maxima. So one thing you have to note that the total length of the transmission line is 2 meter. So if suppose you have put the value of beta and phi here with m is equals to 0, okay, so you will get the value, okay, which will come something like here because uh, the convention we have taken as z is equals to 0 at the load side and z is equals to minus 2 at the source side. Okay, so first maxima will you will obtain here at z is equals to minus 0.625. So you have to go for, you have to check for another value of m because there may be a chance that maxima will occur at some other point as well. Okay, so yeah, so you have to put the value of m here as 1. Okay, then you will get the value of z max minus 1.875 meter. Okay, so this shows that two maxima will occur in this transmission line having length of 2 meter. Hello, am I audible?
Yes, sir.
Okay, so for similarly you can calculate the value of z min, okay, by using this equation. Okay, and you have to just put the value of 0 1 2, so you will get the value of z min as this one. Okay, so any doubt in this question?
Sir, how did we take value of phi equal to pi, sir? Can you
Phi
please
is
explain?
equals to pi. Yeah, see, basically phi, value of phi depend on the phase term that is obtained from the yeah, reflection coefficient. Okay, so here gamma is obtained as minus 1 by 3. Okay, like here minus
Sir,
1 by 3.
okay. Right?
Yeah, so
Okay,
phase.
thank you, thank you.
Okay, okay,
Got it, sir, got it.
okay. Any other doubt?
No, sir.
Okay, so this is the next question. In that a 100 ohm transmission line is operating at 2.5 gigahertz frequency and has an effective dielectric constant of 1.65. Find the smallest open circuited line. Okay, find the smallest open circuited line of this line that appears at the input as the capacitor of 5 picofarad at 2.5 gigahertz. Okay, so basically this is a combination of two questions. You have, if suppose you have a transmission line, okay, and yeah, the characteristic impedance of this transmission line is 100 ohm and it is operating at 2.5 gigahertz, having dielectric constant of 1.65. Okay, so you have to you have to obtain the length of the transmission line from the load side, where you will get the input impedance as the capacitance, same as the capacitance. Okay, this will be equal same as the sorry, minus 1 over j omega c, where the value of c is given here, which is equals to 5 picofarad. Okay, so you have to calculate the value of this line length such that you will obtain uh, the capacitance value at this input. Okay, similarly you have to perform this exercise for inductance of 5 nanohenry. Okay, so see, first of all, this is a open circuited line. It is given in the question. Okay, so for an open circuited line, we can see that the ZOC is defined as minus JZ naught cot over beta L. Okay, which will be same as minus J over omega C. So operating frequency is known to you, and how much capacitance you want, that is 5 picofarad. Okay, this parameter is also given to you, so you have to first calculate the value of this input impedance by using the value of capacitance given to you. Okay, this will be same as minus j z naught cot over beta L, the input impedance of the transmission line. Okay, so I'm just equating these two terms. From there you I can get the value of beta L, and beta, as we know, can be calculated by using the equation 2 pi by lambda. So see here, lambda is basically defined as v by f. Okay, and this v basically uh, given as 2 pi f root over epsilon r by c. Okay, so by using this equation you can obtain the value of beta. Okay, so once beta will be known, you can compute the value of length. Okay, so that's how you can calculate the value of line length, which will get which will give you a particular value of impedance. Okay, similarly this
Yes, sir.
exercise, yes,
Yes, yes, yes. Okay, carry on, sir.
Okay, so similarly, you can perform this exercise for calculating the value of inductance. So, as you know that for inductance, the impedance is defined as j omega L. So, omega, you know, L is already given to you. Okay, so that's how you can calculate the value of uh, yeah ZOC. Okay, which will be equals to minus sorry J 78.5 ohm. So this will be remain same as minus j z naught cot over beta l. So from there you can calculate the value of beta l, and beta you have already find from the previous question. That will not be changed because parameters are same here. So that's how you can define the you will get the value of line length of this transmission line, where you will get the inductance. So that's how you have to proceed such a question. Any doubt in this question?
No, sir. It's fine.
Okay. So the next question is similar to the previous question. So I am leaving this to you as an exercise. Okay, you have to solve it by yourself. And if suppose you are unable to solve it, then I will give you answer. Anyway, this slide will be provided to you. Okay, so you will get the answer there, but I think you have to first to solve it by yourself. Okay, so I am reading this question. If you want, you can write it. A 100 ohm transmission line operating at 2.5 gigahertz frequency and has an effective dielectric constant of 1.65, same as the previous one. Find the smallest short circuited length of this line that appears at the input of the capacitor of 5 picofarad at 2.5 gigahertz, and repeat this for obtaining an inductance of 5 nanohenry. So the question is remains the same here. This one, okay. The only thing is that this time we are uh, short circuiting the load. Okay. In the previous case, we the load is open circuited, but now this load is short circuited. So the problem is almost like same. You have to just change the value of input impedance. There we have taken the value as minus j z naught cot over beta l, but for short circuited impedance, input impedance is defined as short circuited line my j z naught tan over beta l. So you have to equate the value of capacitance and inductance with this j z naught tan over beta l, and you can then find the value of line length. Okay, so this you can do it by yourself first. So this is the last question, I think. So the question is, the transmission line circuit in the accompanying figure has Vg of 15 volt, which is the RMS value. See here, this is the RMS value, not the peak value. And Zg is 75, Z naught is 75 ohm, and ZL will be 60 minus J40 ohm. Line length is given as 0.7 lambda. So you have to compute the power delivered to the load. So any idea that how to proceed?
So first we'll find the reflection coefficient.
Yes. After that, yes, you are almost there.
From that, after that, input power.
Yes, yes. See, if suppose you have computed the value of reflection coefficient, then you have to just find out the value of input power to this transmission line. Then you can use this relation. sorry, you can use this relation PL is equals to 1 minus mod over gamma square into P in, as we have seen in the previous numerical. Okay, so by using this
Yes, sir.
relation you can find out the value of uh, load power. Okay, so let us see here. So see, reflection coefficient, I think you all can find out. Okay, because relation is same, you have to just put the value of ZL and Z naught, and after that you will get the value as 0.303 phase minus 94 degree. Okay, now the thing is that how to find the value of input power. Okay, so for finding the value of input power, you have to first consider the case when this signal is just approaching this transmission line. This input signal is just approaching this transmission line. Okay, so what impedance this input signal will see? It will be same as the characteristic impedance of the transmission line. Okay, so you can now use the voltage divider rule so as to find the value of voltage that you will obtain at the input side when there will be no reflection, let us say, because you have just encountered this voltage, you have just connected this source to this transmission line, so there will be no reflection will become after certain time. Okay, but till now there will be no reflection. So by using this voltage division rule, you can find out the value of V in. So V in is defined as Z naught over Z naught plus Zg into Vg. So this will be your input voltage. Okay, which will be 7.5 volt. Okay, so input power is defined as V in square over Z. Okay, this will be equals to 0.7 watt, 0.75 watt. Okay, so now you can use this relation and you will get the value of load power as 0.68 watt. Okay, so for verifying this load power, we can also use some other method, like we know that load voltage is defined as, yeah, line voltage uh, in line voltage is defined as V of Z is equals to V naught plus uh, sorry, e raised to the power minus j beta Z plus V naught minus e raised to the power plus j beta Z. Okay, so at the load end, what will be the voltage? So how you will get? Simply you have to just put
Z
Z is equals to 0. Yes, you
Z
are right.
equal to 0.
So this will becomes equals to V naught plus V naught minus. Okay, any doubt?
No.
Yeah. So see, reflection coefficient you can calculate at the load side. Okay, which will be given as gamma is equals to ZL minus Z naught over ZL plus Z naught, which you will already calculated here. Okay, so you have to just put the value of gamma here. Okay, so V naught plus is already known to you. You have already obtained this V naught plus, which is equals to 7.5 volt. Okay, you have to calculate the value of load voltage by using these parameters. So this will be becomes equals to 7.68 magnitude, and phase will be minus 17.16 degree. Okay, so now load power is defined as I square R, you all know. So I you can calculate it as load voltage divided by load impedance square. Okay, and see load impedance is given here, which is a complex number, and the power is delivered to the load only just because of the real part of this impedance, which will be 60 here. So by using this relation, you can find out the value of load impedance. Load power, which will remains the same as 0.68 watt. See, so that's how you have to proceed with this question. So any doubt in this question?
Sir, initially you told that uh, the source will see the characteristic impedance as the generator will see characteristic impedance, but I think the generator should see Z in as the impedance connected to it. Na?
No, 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 no. See, Z in, when Z in will play. Okay, whenever there will be a reflection associated with it, then only Z in will be uh, uh, Z in will come into picture. Okay, but till now
Acha.
see, this signal is not approaching at the load side till now. Okay, then there will be no reflection.
We are considering the transient condition.
Yeah, you can say the transient condition. It is just the uh, initial value. Say you have you just see, right now you connect your voltage source to the transmission line. So what happened? Or you can say you have connected one switch here. Okay, so you have connected one switch here. So at t is equals to 0, you close the switch. Okay, so how much
Mhm.
impedance the source will see? It will be same as the impedance of the transmission line.
Hmm.
Okay, so that's how you can calculate the value of V0 plus.
Okay.
Any other doubt? So if there is
No,
no
sir, it's
doubt,
fine.
then I think we can wind up this session.
Okay, sir.
Thank you. Thanks all.
Thank you, sir.